Greetings again. So this would be my video class for the third week of classes. And in this particular video, I'm going to talk about work functions and service time functions. Also about power as one of the metrics of performance. So work functions are a generalization of the work metric that we talked about last week. And we make this generalization so that we can define work over a continuous domain of time as opposed to discrete points in time. And this makes work functions easier to handle. Their handling becomes somewhat more straightforward because we could apply all the power of calculus and mathematics to relate things together, as you shall see in just a little bit. So we could say that a work function, WT, is a non-negative and non-decreasing function of time for all t greater than 0. So we don't want work function to be negative, and we don't want it to decrease. So it's sort of like a cumulative quantity that is built over time. And as time progresses, we kind of get more and more work done. And the work we do, we never lose. So as this statement here indicates, work function specifies the amount of work that is completed by a system up to and including time t. So here are some examples, like Wt is equal to t, or Wt is equal to 4 t squared over t squared plus 1, and Wt is equal to t minus sine t. So these are work functions that are non-negative, and they are also non-decreasing. And you can actually check that simply by taking the derivatives and showing that the derivatives of all these functions remain positive for all t greater than 0. And so the marginal throughput of a work function or marginal throughput function that is derived from a work function that is performed for a system is simply the derivative of the work function, as it is written down here. Just basically the limit of the difference of the work function as we transition from time t to time plus delta t, and let delta t kind of tend to 0. So taking the derivative of these functions that I've written up here, we come up with values that are throughput functions for these three work functions that we defined up here. So in the first case, our throughput function is equal to 1, which simply means that as work itself grows linearly with time, the throughput is increasing, it remains constant, that is. That is to say, the rate of change of t, the work function, that is constant. So it's really a line, as it is here. And in the second case, the derivative of the work function becomes this quantity, this formula, which again, for all t greater than 0, is clearly greater than 0. And the same is true for this particular function. So you can see that we very easily derive the throughput function from the work function, and this makes the analysis of these two functions closely related and easier to handle. Now we can also compute, once we're given a work function or a throughput function, we can compute the total work between two periods of time, for example. So here we have specify the time changing between T1 and T2. And so what we do is we put the throughput into our integral, and keep in mind that throughput is work over time, so these things cancel out. Effectively, we're just summing over this time period all of the incremental pieces of work we do, and that is the throughput, of course, and that gives us the total work. And of course, when we want to consider total work between time 0, let's say, and time t as t tends to infinity, then we need to compute this limit, which is our total work for as long as time runs. And the average throughput between time t1 and t2 would again be given by total work we do over this time period, that is time that runs from t1 to t2, divided by the difference of the two times. So again, this is the rate of work to time. And we can also find the average throughput by letting time tend to infinity and then integrating the throughput function from 0 to t. And as of course t tends to infinity, and then of course dividing this whole thing by t and taking the limit in that fashion will give us the average throughput. So you could see, as I said earlier, that these things can be computed rather easily once we lay the foundation for continuous work functions. So here's a simple example. The throughput of a processor is given by this expression, where you could see that the throughput kind of sort of like at time 0, it is actually equal to 0, but then after that the second term tends to very quickly tends to 0 as t tends to infinity, and this sort of like disappears, and then our work tends to 10 to the 9 as t, our throughput that is, tends to 10 to the 9 instructions per second as time tends to infinity. It kind of stabilizes to that. So initially it begins as 0, kind of goes up very gradually, very rapidly I should say, and then ultimately settles to 10 to the 9. So you could attribute this to maybe the machines get into a ready state and so on, but that time is supposed to be fairly small. So to compute work, for example, between time 0 and time 10, we take this function and simply integrate it to compute the work function. So we take it, integrate it, and we get this function out of the integration, and now we substitute the values of 10 and 0, and that gives us about 10 to the 10 instructions total is what we get to execute in 10 seconds. And this I think is reasonable, as I said, as I predicted that this will tend to 0 very quickly at the end of 10 seconds. This will be very, very small. So effectively we're executing 10 to the 9 instructions, and in 10 seconds that will be 10 to the 10, which is what we roughly get here. And of course we want to compute the total work. Then we have to take this limit, so we go ahead and do that. And as you can see that the work tends to infinity, total work as time tends to infinity. And this is again reasonable because this is a system that will pack 10 to the 9 instructions per second, so as we let the time tend to infinity, there's no bound on the number of instructions that we're going to execute. So it tends to infinity as time tends to infinity. That is the work. So there is an analogous concept. In fact, we already saw this when we talked about throughput versus service time, or average service time. And we had that reciprocal relationship. So to get to that place, what we want to do is to extend this notion of service time to a continuous domain of time. Service time itself is sort of like in a way, is an amount of time that varies um, with time. So I should really not say continuous time. I just have to fix this continuous work, not time. That's the only way this will make sense. I just caught myself making a mistake there, and then I fixed it. So as opposed to having discrete work and then measuring these times at different amounts of work and then computing the service time, averaging it over work, we really take this time to be a continuous function of work. And that's how we write it. So it becomes effectively time that varies over work. And it is also non-negative, and it also increases. This time, as we do more work, never decreases. It actually keeps going up. And we have that sensation anyway with time. Time always goes up and runs along. So, and I guess this W0 is something that's a leftover here, which I can remove from there, because I actually set that to 0 in this situation. So we could say that the service time, just to recap, is a function of work, and it is non-negative and increasing in time, in work. As work increases, then time increases. It's kind of interesting in a way because we're doing some work, and kind of the work itself marks the time. If we didn't do any work, put it the other way around, and if that's the only way we can tell the time will kind of like stop. So what really makes time tick is what we do with it. That is, what work we produce. Now, so we could say that the service time specifies the amount of time that is used by a system to produce a work of W. And so we can write, for example, time of W is equal to W. And we could also say time of W is equal to 2W squared divided by W plus 1, square root. These are proper time functions. They are non-negative, and they actually increase over time. And marginal service time is like the marginal throughput, or just the throughput of a system, which is denoted by tau of W, under a service time function T of W, and at work W greater than 0, is given by the derivative of time function, that is service time function, and that is to say that tau of W is equal to TTW dW, which is again a limit of a difference function divided by delta W. So in the first case, the derivative of TW is equal to 1. That means our service time actually sort of grows linearly with work. In the second case, we take the square root. We take the derivative of this TW with respect to W, and then we arrive at this formula, which again is something that shows that this function is non-decreasing, as this is actually positive for all W that is greater than 0. Okay, so now you could see that the work function and the service time function as a function of time provide us valuable representation that we can use to compute service time and work functions, work amounts. Now, we could also relate average throughput and average service time together, but to get to that, we really have to relate, first of all, the marginal service time to marginal throughput. And you can see that by definition TW is equal to dt over dW, which we can then write as 1 over dW over dt, which is then clearly 1 over xt. So this is kind of a transformation from the W domain to the T domain. And of course, for this to happen, we have to have dW over dt well defined. So here's an example. We're given a work function, 3t plus 2, for all t greater than or equal to 0. The service time function then is given by t of w, which you just obtained by solving t here in terms of w, and you get this formula. For w greater than or equal to 2, this function then is clearly non-negative and non-decreasing for all w greater than or equal to 2. And it's also differentiable everywhere with marginal service time of 1 over 3, which is equal to 1 over xt from this expression. Because if you take the derivative with respect to time, you get 3, and that is 1 over 3 is what we then get for the average service time, which you could have also gotten directly from this formula by taking the derivative of the right-hand side with respect to w. So if you cannot extract the service time from a work function, and then you can use implicit differentiation rule in order to be able to compute the marginal service time, if you like. In other words, you could use this relationship that the TFW is equal to 1 over xt. If you know how to compute xt because you're given a work function, then the TW would be 1 over xt. Okay, now relative performance is something that we could actually relate to because we've done this last week when we looked at discrete work functions. So what we're really doing here in order to define what we call fixed time work gain, we are fixing the time on two systems, and we call them A and B, and then we look at the potential gain, work gain, of the first system, that is system A, over the second system, and with the throughput functions that are given by x of A of t, x of B of t. So the gain itself will be just total work done by system A in this time period from T1 to T2 divided by the work that is done by system B during the same time period. And of course that will give us the work gain if we have any. Now if we let T1 equal to 0 and T2 equal to capital T, and then the work function of 0 for A and B, they both are equal to 0, then this formula reduces to this expression where we're taking the limit of work of A over T divided by work of B over T as T tends to infinity. So we kind of look at total work done over an infinite amount of time and take the ratio. That's the work gain. I guess this relative performance is very much like, when we fixed the time and looked at the ratio of work. And it is just generalized to work functions of time. Now, we could also do what we call fixed work time gain, which would be really nothing but speed up. And to get that, we need to work with the marginal service times. And also we have to be a little careful about where these terms go. In the work function comparison, that is work gain comparison, we actually put the A at the top and B at the bottom. But here we kind of put the B at the top and A at the bottom because we're looking at the gain time-wise, speed up of A over B. So B must go up. And if this ratio is greater than 1, we know that A is better than B. And that's how we want to interpret this ratio. With greater than 1 simply means A is better. Less than 1 it means that B is better. So when you do the integral, for each of these, then you get the T of B. This was tau of B, and now I get T of B. That's the integral of actually tau of B. And of course, you evaluated at two values. Again, when we let W1 equal to 0 and W2 equal to W, and then set these initial conditions on the and this actually not be tau but t, it should be. Let me just do that correction here. Just a minor mistake I have here, and that takes care of that. Now, so you could see that we're basically letting these to be 0. I guess the same correction would have been made, but we did make that correction. We did actually have it right here. Okay, so we made that change, and now we have set these equal to 0. And so then the work function becomes work gain, that is, of A over B. That's what this stands for. Not work gain, I'm sorry. The time gain is what it is. The time gain, the speed up, is equal to basically limit of the 2 times B over A for work as work tends to infinity. So this is really time gain, not work gain. Work gain was the one that we talked about on the earlier slide. So, but they're similar. The only difference is that there's an A here, there's a B, and here there's a B, here there's an A. So just make sure that you remember that, because when you measure time and you take the ratio, you want B to be at the top and A to be at the bottom, because if B is larger than, that is T of B is larger than T of A, then clearly you're doing better as system A than system B. That's going to give you some quantity that's going to be greater than 1, and that's what you want to do. So that's just that. Now there's also, before I go to that, maybe I'll just give you this example. So here's the work gain and time gain illustration. So if I put the work functions to be these functions here, 2 work functions, then the work gain of A over B would be log t plus 1 minus log 1 divided by square root of t minus square root of 1. We just simply put these work functions to work on the numerator and the denominator. That's how we compare them. And then we get this, this expression. I guess there's just one small mistake here, which is really nothing serious, but I got to put minus 1 in there because it seems like he started out at okay, actually this is correct in a way because we are using t equals 0 here. When we do though, this is fine. This is absolutely correct. So what we have here is that we just substitute t equals 0 for this case. The only thing that this should be equal to 0. So let me just make that change. The only change that I'm going to have to make, if this could be made. See if it is going to work somehow. If not, I just have to get this removed from here. Seems like I may not be able to get this to work. Yep. Alright. Essentially, what I'm just saying that you should just knock this out, but that's perfectly alright. As t tends to infinity, this goes to 0 because we know that log function always grows more slowly than the square root of function. And time gain, we then take these work functions and create their time function equivalents. And so just this, of course, will give you e to the w plus 1 again. I think I'm just made some mistakes here. Let me just go ahead and put that plus 1 in there. If I could, this has to be changed. Okay, I was able to get this one somehow. I can just get up to that, and w plus 1 seems. So that's been fixed. I don't know why I couldn't fix this other one here. This is the one I wanted to change. Let's see, it doesn't. Oh, it did come up. So I just have to take this out of there. It seems like I don't need it because my function itself is just square root of t. Okay. So now we are in business, and we then made these transformations. So we get the functions in terms of w. And then all we have to do is just now express these times um, because we're looking at the time gain. We put this at the top and we put this at the bottom, and then we get this ratio, and the ratio basically, as we substitute W equals to 0, W is equal to W, capital W that is, we get these ratios, this one and this one, and that tends to 0. So what this really tells you as W goes to infinity is that the two metrics of performance are consistent, because what this is saying is that a system A is actually worse than system B when it comes to work gain, because you gain 0 as system A over B. That's what this is saying. Basically, you don't have any gain. And then here it says that the time gain or speed up of A over B is also tending to 0. So B is superior in both senses of the metric that we're using here. Both metrics tell us that B is better than A. That's what we conclude. Now, there's also the throughput gain, and this is now a comparison of two throughputs, and this is where we may have some issues, but let's just define it first of all. So what we're really saying is we take the limit of the throughput for A as t tends to infinity. We do the same for B, and we take the ratio, and we call that the throughput gain. So we individually compute the throughputs for A and B, and then we take the ratio of the two. And so this metric basically gives us the capability to determine the performance-wise, the relative performance of the two systems. So the only thing that you have to be careful here, as I actually talked about in class, is the so-called ratio gain. And the ratio gain that is illustrated here is as follows. So we have two systems, system A and system B, and they work for 1 second for each type of work they work on, which will be A work and B work, type 1 work, and type 2 work. So system A works on type 1 for 1 second to produce 20 work, whatever the unit of work here in this case is. And then we actually do the same for type 2, and then again in 1 second, system A produces 10 work. So 20 work and 10 work for system A in each of those seconds. B then takes the same 1 second but produces 10 units of work of that same type that A produced 20 units. And their roles are reversed here. Of type 2 work, B actually produces 20 units of work, whereas A had produced 10. So now we can write these throughput functions, throughput ratios, like A over B for type 1 is equal to 2 because that's 20 over 10. That is 20 units of work per second and 10 units of work per second. So that ratio is equal to 2. But then in the second case, that is where this 2 comes from, the work gain would be 1/2 because A actually produces 10 units of work, whereas B produces 20. So that's 1/2. So now you can say average throughput, therefore, added to and divided sum by 2, and that comes up to 25 here, not 15. See if I can actually change that real quick. And this is also the same. So what we get then is that a suggestion that A is better than B in this comparison, but by the same token, now here the throughput gain of B over A for the first type is actually 1/2 because B is doing 10 and A is doing 20. And here, of course, it's the other way around, because B is doing 20 and A is doing 10 in the same 1 second. And therefore, average throughput will be 1/2 plus 2 over 2, and it's going to be 125. So this will tell us that B is better. So that's what's called a ratio gain. We take the ratios of throughputs and then conclude in two different ways. And of course, we know that both systems have the same performance in that they both do 30 units of work in 2 seconds. That means they do 15 units of work per second, and therefore they actually have the same throughput in an average sense. So that's the only danger, that when we actually take these throughput ratios and then sort of like add them up randomly. Now this formula doesn't suggest that at all. In fact, this is the right way to do it. We compute the total work in a way, normalized to time, same amount of time in both cases, and the consequently, you're going to have the right comparison here, because you're taking the integral as opposed to like adding them up and then taking the arithmetic mean that we were doing here, which we should not have done. That's what people do to play the ratio games. Now, let us kind of slowly change the subject to what we call the CPI, which is really a rate of sorts. It's kind of like throughput or service time, I should say, in some sense. And how is it? Number of clock cycles is obviously going to give us time somehow. When we take that number of clock cycles and divide it by the frequency of our clock, which will be number of clock cycles per second, so we get seconds out of CPI. So CPI is the number of clock cycles divided by number of instructions that we execute during that number of clock cycles. And then we can compute from that average. This is an average, clearly, because we counted the number of clock cycles, and then we counted the number of instructions, and then we take the ratio. That is a rate. That is actually an average in a way. And then we take that average divided by the frequency of our system to get ourselves the average execution time. That same average execution time then is equal to simply by a way of CPI, just take that CPI and then just take it as NC over NI. There's something that is actually a little bit erroneous here, it seems. Let me see if I could just quickly fix it. CPI is equal to NC over NI. And this is actually total. This is not average. So in that regard, this is correct. So we take the number of clock cycles and then divide it by the frequency. That gives us the total time of execution. Again, number of clock cycles is for the entire computation. This is average. So this formula is correct. And now this, of course, we can replace NC by CPI times NI. And you can see that then gives us simply from this formulation CPI over F is equal to TS, and then we get TS bar, that is TS bar, times NI. So if you know the average execution time and you take the number of instructions, that gives you the total service time. That's what this is saying. And finally, the speed up can be expressed as the ratio of time B, speed up of A over B will be just TB over TA. And then we can actually use this formula here to generate this formula, this equation. But what you really have to watch here is this. When you're looking at speed up of A over B, then you have to relate to these terms as follows. You have to say that if the number of clock cycles per instruction for B is larger, then speed up of A over B must be larger. So it goes in the numerator. And by the same argument, CPI A goes in the denominator, because the larger this is, the smaller that the speed up becomes. Okay, and the same goes for the number of instructions that B executes. As that becomes more, then the speed up uh, becomes more for A over B, and as an A, that is number of instructions for system A goes up, then of course speed up suffers. And finally, frequency is the same way. The higher the frequency of system A, the better the speed up is going to be higher. And that's how this ratio. So you could really relate to all this stuff. And that's what this formulation is all about. So this, I think, completes our discussion of work functions and, work gain, time gain, and throughput gain, and finally another metric, a more closely related to computers, which is the number of clock cycles per instruction, which is basically some sense of service time averaged over all the instructions we execute. So if you take all of the instructions, number of instructions executed as your work, and then this clock cycle, number of clock cycles as a measure of time, given that you know the frequency of your system, then that is more like throughput. So the only thing that is left to discuss here is the energy and power metric. So for that, I introduced this model in class, and we have a voltage source and we have a processor. So voltage source, by way of the charges it contains in it, sort of like sustains the processor for its energy consumption. And so there is a current that flows into the system, and basically the rate of change of charges over time is what this current is. So that means charges flowing into the processor to energize it for it to make the computation. And so we could actually say total energy across this voltage source will be the potential it holds times the charge it actually discharges at time t, or up to time t, that is. So this is the energy consumed by the processor, if you like, or released by the voltage source over a period of time from 0 to time t. And so QT is the total charge used by the processor in that time period. Now the energy consumed between time t0 and t1 will then be given by dE dEt, where ET goes from ET0 to ET1. And then we can actually replace this by V dQt, and then replace the QT by the boundaries by QT0 and QT1. And that becomes the integral of V IT dt, because that's how dq dt is expressed. So this is really equal to it is equal to dq over dt. Therefore, dqt is equal to it times dt. So now we have a power t, and that's really what the energy, the formula for the energy computation from t0 to t1. So we kind of like wrote this in a long about way, but effectively this is saying that total power, energy rather, consumed between time 0 and time 1 is really equal to integral of the power function from t0 to t1 over t. So this is useful in the sense that it kind of nicely relate things together, and makes the energy function kind of analogous to work function, and then P itself is analogous to the throughput function. And we can also compute the average power consumed by the processor simply by computing the total energy consumed divided by T. And you can see that that's really the energy consumed between time 0 and time t divided by t as t tends to infinity. So here is an example, and this example basically something that's also in my lecture notes, as well as we discussed this a little bit towards the end of the second class during the third week. So if we just say that a processor is powered by a 5-volt battery and draws 0.1 amps to compute 1 million additions in 0.5 seconds, how much energy does the processor consume for each addition? How much charge does it use? I guess in the class I didn't really put these many additions. I just simply used one addition, which would have been erroneous. So I stand corrected here. Anyway, so the energy itself will be just power multiplied by the current and multiplied by the time. That's like total charge, which this is, times the voltage is the energy we consume. And of course, we normalize it to 1 million additions. And so the number comes to 0.25 times 10 to the minus 6 joules, or 250 nanojoules per addition, which is kind of reasonable. And with an average power of 0.5 watts, which comes out of the formula here. Now, the battery discharge would be simply to take the amount of amps we consume over the time period that we run it, and then multiply it by the number of elementary charges in a single coulomb, which will be this formula here, and so when we do, you get yourself a 3.121 times 10 to the 11 elementary charges per addition. And so that is a lot of charges. So just to do one addition, we really consume 10 to the 11, even more than that, elementary charges. So ideally, you'd like to think that you could just use one charge, whether it's the charge of an electron or charge of another charged particle, like proton and so on, and just one of those should be enough to do one addition. We're nowhere near that, so we have a lot of time to go to reach that point, that goal. So the last thing that I want to say here, I guess, is that as in the case of throughput and service time, the relation between the amount of computation performed and energy consumed by a processor can also be examined in terms of the number of operations averaged over the energy it uses. Okay, so to say that the processor consumes 0.25 10 to the times 10 to the minus 6 joules, which is 250 nanojoules, as we said over here, is equivalent to saying that it performs 4 times 10 to the 6 additions per each joule of energy it uses. That's just like another way of looking at it. I also mentioned in class, I guess as one last item, a formula that relates work and energy together. So I just said that there is a correlation between the work that is produced, in this example would be just the number of additions, and the energy consumed. So we can technically say, as I wrote in class, that work produced is a function of energy used. And I actually wrote that in class as W time, that is the work that is generated up to time t, is some alpha of t times energy of t, where this alpha of t is also something that varies in time. And when we make that alpha t constant, we can now see that the derivative of the work function, which is our throughput, then becomes proportional to the power that is consumed by our system. So that relationship is fundamental in that it really tells us how effectively we're able to use each charge, each coulomb of charges in order to generate useful or just computations, basically. The inefficiency will derive from the fact that there's a lot of heating in the system, and that we could tell simply by the amount of work we get done by as opposed to the amount of energy that is pumped into the system. We talked about this in class, so I'm going to leave that alone, and then so we're going to go into home assignment 2. And so for this one, we're going to look at problems 1A, 1B, 3, 4, 7, 9, 16, 26, 27, 28, and 30. And I state that each problem is worth 10 points. So there's a lot of questions. You may want to get to them fairly quickly. These are problems that are coming from the lecture notes. If I could really get my hands on those quickly. Let me see if I can just find this. There's the performance chapter right there. And so if I can go to the first set here, we're talking about these problems here. So it begins on page, which page is this? Let's see, page 11. I guess it's page 11. Page 12 is where it begins. So you have to look at page 12 and down to find out where this thing is. As I was looking at the PowerPoint presentation here, I said problem 1A, 1B, 3, 4, 7. So 1A, 1B, these are the problems like 1A, 1B, and then 3, 7, 3, 4, 7. Here's your 4, 3, and 4, and then 7, and then and it goes all the way up to 30. 30 will be, I guess, somewhere here. That last problem must be here somewhere. So these are the problems that I expect you to work on until February 26th. So you would have effectively time between, let's say, tomorrow, that is Wednesday, and I guess February 26th, that would be also a Wednesday. Okay. So 1 week of time is what you need to get these problems done. And so you have to, you had a lot of time to get the first homework submission. This will not be as long, so you may want to adjust to that. All right, well, I think this completes our video lecture for the third week of classes, and I'll see everybody tomorrow in class at 11 a.m. Until then, take care and good night.